Hello my dear students, I warmly welcome you to SIA's digital classes. In this lecture, we are going to discussing about special linear group. Okay, so let's see the theorem. Show that special linear group of 2 by 2 matrices over rational numbers is non-abelian group under matrix multiplication. That is the first question. Or else in the examination, okay, show that the set of 2 by 2 matrices with determinant 1 with entries from rational numbers is non-abelian group under matrix multiplication. Okay, in the examination we have two ways to ask the question in this format. The first question is this one, okay, and the second format is this one. This second format question has asked in the this year 2022, okay, June examination of algebra from Usmania University. Okay, so now we are going to discussing about special linear group, and we are going to prove that this special linear group is a group and not a abelian group. Okay, so first of all, as we discussed in the introduction classes, okay, so I am explaining briefly about special linear group once again. In this special linear group, mathematically we can denote it as SL of 2 comma capital F. Okay, here you know S represents special and L represents linear, and this pair represents group. Okay, special linear group of 2 represents the order of the matrix, 2 by 2 matrices, and here capital F represents the field. That means set of real numbers, okay, set of complex numbers, or set of rational numbers, or set of integers modulo p. These 4 fields you can face the examination. Okay, in this question is asking, okay, we have to prove with respect to the rational numbers. Okay, in this question he is asking with respect to the rational number, that is we are taking f equal to capital Q. Q is nothing but rational number. So now you can see here, okay, so now SL of 2 comma F is equal to, I am writing the original definition, flower bracket A B C D. Okay, it is a 2 by 2 matrix such that the elements A comma B comma C comma D belongs to rational numbers with their determinant. Okay, AD minus BC is always is equal to 1. AD minus BC is always is equal to 1. Then these types of matrix, if they form a group, that group is called special linear group of 2 by 2 matrices with respect to rational numbers. Okay, so now we are going to prove this SL of 2 comma Q. Okay, so now I am writing claim. Claim is nothing but what we are going to prove in the theorem. Okay, so that is I am writing clearly S L 2 comma Q is non-abelian group, is non-abelian group. So we have to prove this condition. Okay, so now to prove this condition, okay, so before going to prove this special linear group is non-abelian group, so you need to know the basic thing is the set of positive rational numbers, okay, forms a group under multiplication. Okay, so the set of positive rational numbers forms a group under multiplication. Now to prove the given condition, so first of all we are going to prove this special linear group is a group. In the process only, so first of all I am taking that closure condition. Okay, so here this theorem we are going to prove by taking the matrices, those matrices of order 2 by 2 only. So therefore that matrices we are going to denoting with capital letters A, B, C only. If they ask in the element formats, we can take small a, small b, small c. Okay, so now closure property, let capital A is equal to A1, B1, C1, D1 is a matrix, and capital B is equal to A2, B2, C2, D2 is another matrix. Okay, these two matrices belongs to SL of 2 comma Q, where where A1 comma B1 comma C1 comma D1 and A2 comma B2 comma C2 comma D2 belongs to rational numbers only. Okay, and with the condition their det A1 D1 minus B1 C1. Okay, so therefore is equal to 1. Det means det of capital A. Here I am writing det of capital A is equal to A1 D1 minus B1 C1 is equal to 1, and I am again writing det of B. Okay, so A2 D2 minus B2 C2 is equal to 1. Why? Because if you take any matrix, the determinant of that matrix is equal to 1, then those type of group is called special linear group. According to the definition only we are taking. Okay, just remember these two values. A1 D1 minus B1 C1 is equal to 1 and A2 D2 minus B2 C2 is equal to 1. Okay, so we took capital A and capital B. Now we are asking with respect to matrix multiplication. So therefore take their multiplication. A into B is equal to. Okay, so A into B is equal to A1 B1 C1 D1 A2 B2 C2 D2. If you multiply them, okay, so you know very well 2 by 2 matrix multiplication. A1 A2 plus B1 C2 A1 B2 plus B1 D2. Next for this row, these two columns, so C1 A2 plus D1 C2. Next C1 B2 plus D1 D2. If you observe carefully, the resultant matrix also a 2 by 2 matrix. The resultant matrix also a 2 by 2 matrix. So therefore, if you multiply any 2 by 2 matrices, the resultant matrix also 2 by 2 matrix. So therefore, this matrix also belongs to special linear group of 2 comma Q. So therefore SL2 comma Q is closure. With this condition, we can say that SL2 comma Q is closure. Now the second condition is associative. Associative condition. In this associative condition, we have to take three matrices. The first matrix is capital A. Okay, A1 B1 C1 D1, and capital B is equal to A2 B2 C2 D2, and capital C is equal to A3 B3 C3 D3. Okay, by using these three matrices, directly I am writing the property. Okay, A into B, first two matrix multiplication into C is equal to A into B into C. From the closure property, you can observe the product of A into B is again a 2 by 2 matrix. Okay, that 2 by 2 matrix, if you multiply with C, that is also 2 by 2 matrix, then the resultant product also you will get one 2 by 2 matrix. Okay, so next here you have capital A is a 2 by 2 matrix, and the product of two 2 by 2 matrices, again you will get one 2 by 2 matrices. The resultant matrix will be 2 by 2 matrices, that is LHS is equal to RHS. In this case, so if you face any question in the special linear group, especially associative property, you have to write it is trivial. Okay, so it is trivial. Associative property is trivial whenever closure property exists. So therefore SL comma 2 comma Q satisfies the associative property. Now the third condition is identity. So in this condition, so the identity condition is let capital A is equal to A1 B1 C1 D1 belongs to SL of 2 comma Q. Okay, then A into capital I is equal to I into capital A is equal to capital A. This is the property for identity condition. Okay, now I am taking that LHS. LHS is nothing but A into I is equal to capital A. Okay, so we have capital A value, substitute A1 B1 C1 D1. Okay, into, we don't know identity matrix, but in RHS we have capital A again, A1 B1 C1 D1. If you think logically, the only matrix that is a possible matrix to obtain here is identity matrix. In place of capital I, we have only 1 0 0 1. That is called identity matrix of this special linear group. You can also cross check. Okay, if you multiply both of them, you will get this matrix only. So therefore, capital I is equal to 1 0 0 1 is the identity matrix. Okay, is the identity matrix. Because we are discussing about matrix, we are calling it as an identity matrix. Otherwise, it is identity element. So therefore, this is I equal to 1 0 0 1 is the identity matrix. In the next fourth condition, we have inverse. Okay, so in this inverse condition, let capital A is equal to, okay, so A1, B1, C1, D1 belongs to SL of 2 comma Q. Okay, so here det of A, again I am writing det of A is equal to mod det of A is equal to A1 D1. Sorry. Det of A is equal to A1 D1 minus B1 C1 is equal to 1. Then there exists A inverse for capital A such that the condition is A dot A inverse is equal to A inverse dot A is equal to capital I. A dot A inverse is equal to A inverse dot A is equal to capital I. This is the inverse condition with respect to matrix. Now I am taking that LHS. So here A into A inverse is equal to capital I. Here we are going to find out the inverse of capital A. In this inverse condition, we are going to find out the inverse of capital A. So first of all, I am writing the formula for this inverse. Capital A inverse is equal to adjoint A. Adjoint A by det A. This is the formula. This is the general formula for any 2 by 2 matrix to find the inverse of the matrix. A inverse is equal to adjoint A by det A. Now here to get the A inverse, we have to do two jobs. The one is adjoint A and the second one is det A. Already we have det A is equal to A1 D1 minus B1 C1 is equal to 1. So now you can see here det A is equal to A1 D1 minus B1 C1 is equal to 1. Okay, he is not asking the group with respect to addition modulo P. So if ask addition modulo P, we can write mod P. He is asking with respect to rational numbers only. Then no need to write that modulo P. Okay. So now here you can see here A1 D1 minus B1 C1 is equal to 1 and adjoint A. Adjoint of A is equal to. So therefore you will get what is the A? A1 D1 B1 C1. Adjoint A means D1 minus B1 minus C1 A1. This is the adjoint of A. Now substitute these two values in that A inverse. So therefore A inverse is equal to D1 minus B1 minus C1 A1 by what is the det of A? 1. So therefore A inverse is equal to D1 minus B1 minus C1 A1 is the inverse of capital A, is the inverse matrix, So is the inverse matrix of capital A. Up to here it is clear. So therefore 4 properties: closure, associative, identity, inverse. 4 properties have been satisfied. So therefore you can clearly say that SL 2 comma Q is a group. But our claim is nothing but we have to prove it is a non-abelian group. To prove that condition, okay, so I am taking that fifth condition, that is commutative property. So in this commutative property, so again we are going to take two matrices, that is let capital A is equal to A1 B1 C1 D1 and capital B is equal to A2 B2 C2 D2. So capital A is equal to A1 B1 C1 D1, B is equal to A2 B2 C2 D2. So now I am writing the property of commutative property A into B is equal to B into A. This is the commutative property. Okay. Now LHS. So A into B is equal to, from the closure property, already we did in the closure property, I am writing directly. Okay. So A1 A2 plus B1 C2, A1 B2 plus B1 D2. So C1 A2 plus D1 C2. So C1 A2, C1 B2 plus D1 D2. So this is the AB value. Now I am writing BA. BA is equal to, I am writing directly. So A2 A1 plus B2 C1. Next A2 C1 plus B2 D1. Next C2 A1 plus D2 C1. Next C2 B1 plus next D2 D1. So this is the AB and BA. If you observe both of them, the resultant matrices are not equal. Why? Because so here A1 A2 plus B1 C2 is there. Here A1 A2 is there, but B2 C1 is there. Okay. Here B1 is different value. Here B2 is different value. Here C2 is different. C1 is different. If you multiply them, okay, you will get the different value. So in this format, from the above two result, clearly we can say that A into B not is equal to B into A. So therefore SL2 comma Q is not satisfying commutative property. Commutative property. So therefore, if it is not satisfying commutative property, then it will not be a abelian group. So therefore, SL2 comma Q, special linear group of 2 by 2 matrices over rational number, is non-abelian group. Okay. So this is the proof of the special linear group of 2 by 2 matrices with determinant 1. Okay. If they ask in the with respect to rational forms, you have to do in this format. Otherwise, in the examination, we have other possibility, that is capital S is equal to Z suffix P, where Z suffix P is the group of integers. Okay, less than P under addition modulo P. Under addition modulo P. That means while you are finding the determinant of the matrix capital A, determinant of the matrix capital A, we have to use that modulo P arithmetic process. Okay, modulo P arithmetic process. So when you are going to find out the A inverse, so you have to write in this format: adjoint of A by det A mod P. Okay, this mod P is the extra word whenever they ask field capital F equal to Z suffix P. Okay, so this is the formula. The rest of the process is same. Okay, whenever you ask the same problem, same theorem in the with respect to real numbers, with respect to rational numbers, with respect to complex numbers, we have to do the same process as we discussed now only. Okay, so these are the two different formats with respect to modulo P, without modulo P. So this is about special linear group of 2 by 2 matrices with determinant 1 is non-abelian group, but it is a group. Thank you.